So we'll define the uncertainty associated to a Hermitian operator. And we want to define this uncertainty. So A will be a Hermitian operator. And you were talking about the uncertainty. Now, the uncertainty of that operator, the first thing that you should remember is you cannot talk about the uncertainty of the operator unless you give me a state. So all the formulas we're going to write for uncertainties are uncertainties of operators in some state. So let's call the state psi. And time will not be relevant, so maybe I should delete I'll leave that bar there, just in case. So we're going to try to define uncertainty. But before we do that, let's try to define another thing, the expectation value. Well, the expectation value, you know it. The expectation value of A, and you could put a psi here if you wish, to remind you that it depends on the state, is, well, psi, A psi. That's what we call expectation value. In the inner product notation would be psi, A psi. And one thing you know, that this thing is real because the expectation values of Hermitian operators is real. That's something we reviewed at the beginning of the lecture today. So now comes the question, what can I do to define an uncertainty of an operator? And an uncertainty, now we've said already something. I wish to define an uncertainty that is such that the uncertainty is 0 if the operator, if the state is an eigenstate, and the uncertainty is different from 0 if it's not an eigenstate. In fact, I wish that the uncertainty is 0 if and only if the state is an eigenstate. So actually, we can achieve that, and we sort of, in some sense, I think the most intuitive definition is the one that I will show here, is that we define the uncertainty, delta A, and I'll put the psi here. So this is called the uncertainty of A in the state psi. So we'll define it a simple way. What else do we want? We said this should be 0 if and only if the state is an eigenstate. Second, I want this thing to be a real number, in fact, a positive number. What function do we know in quantum mechanics that can do that magic? Well, it's the norm. The norm function is always real and positive. So this we'll try to set it equal to a norm. So claim it's the norm of the state A minus expectation value of A times 1 acting on psi. This will be our definition of the uncertainty. So it's the norm of this vector. Now, let's look at this. Suppose the norm uncertainty is 0. Then if the uncertainty is 0, this vector must be 0. So A minus expectation value of A on psi is 0, or A psi is equal to expectation value of A on psi. The 1 doesn't do much. Many people don't write the 1. I could get tired and stop writing it. You should, probably it's good manners to write the I, but it's not all that necessary. You don't get that confused. If there's an operator and a number here, there must be an identity matrix. So if the uncertainty is 0, the vector is 0, and this is true. Now you say, well, this equation looks kind of funny, but it says that psi is an eigenstate of A because this is a number. You know, it looks a little funny because we're accustomed A psi, lambda psi, but this is a number. And in fact, let me show you one thing. If you have A psi equal lambda psi, oh, I should say here that psi is normalized. You know, if psi would not be normalized, you change the normalization, you change the uncertainty. So it should be normalized. And look at this. If you have A psi equal lambda psi, do the inner product with A. Do the inner product with psi, comma A psi would be equal to lambda because psi inner product with psi is 1. But what is this? This is the expectation value of A. So actually, given our definition, the eigenvalue of some operator on the state is the expectation value of the operator in the state. So back to the argument. If the uncertainty is 0, the state is an eigenstate. And the eigenvalue happens to be the expectation value. That is if the uncertainty is 0. On the other hand, if you're in an eigenstate, you're here, then lambda is A, and this equation shows that this vector is 0, and therefore you get 0. So you've shown that this norm, or this uncertainty, is 0 if and only if the state is an eigenstate. And that's a very powerful statement. The statement that is always known by everybody is that if you have an eigenstate, yes, no uncertainty. But if there's no uncertainty, you must have an eigenstate. That's the second part, and uses the fact that the only vector with 0 norm is the 0 vector, a thing that we use over and over again. So let me make a couple more comments on how you compute this. So that's the uncertainty so far. So the uncertainty vanishes in that case. Now, we can square this equation to find a formula that is perhaps more familiar, not necessarily more useful, but also good for computations is pretty good. Delta A of psi, which is real, we square it. Well, the norm square is the inner product of this A minus A psi, A minus A psi. Norm squared is the inner product of these two vectors. Now, the thing that we like to do is to move this factor to that side. How do you move a factor on the first input to the other input? You take the adjoint. So I should move it with an adjoint. So what do I get? Psi. And then I get the adjoint and this factor again. Now, I should put a dagger here, but let me not put it, because A is Hermitian. And moreover, expectation value of A is real. So no need for the dagger. So You can put the dagger and then explain that this is Hermitian and this is real, or just not put it. And now, look at this. This is a typical calculation. You'll do it many, many times. You just spread out the things. So let me just do it once. Here you get a squared minus a expectation value of a minus expectation value of a plus expectation value of a squared psi. So I multiplied everything, but you shouldn't be all that. I should put a 1 here probably. Shouldn't worry about this much. This is a number and an a number and an a. The order doesn't matter. These two terms are really the same. Well, let me go slowly on this once. What is the first term? It's psi a squared psi, so it's the expectation value of a squared. Now, what is this term? Well, you have a number here, which is real, goes out of whatever you're doing, and you have psi a psi. So this is expectation value of a, and from the leftover psi a psi, you get another expectation value of a. So this is a. Here, the same thing. The number goes out, and you're left with a psi a psi, which is another expectation value of a. So you get minus a. And you have a plus expectation value of a squared. And I don't need the I anymore because the expectation values have been taken. And this always happens. There's a minus here, and a plus here. So there's just one minus at the end of the day. One minus at the end of the day, and the familiar or famous formula comes out that delta of a on psi squared is equal to expectation value of a squared minus expectation value of a squared, which shows something quite powerful. This has connections, of course, with statistical mechanics and standard deviations. It's the probabilistic interpretation of this formula. But one fact that this has allowed us to prove is that the expectation value of a squared is always greater or equal than that, because this number is positive, because it's the square of a real positive number. So that's a slightly non-trivial thing, and it's good to know it. Now, and this formula, of course, is very well known.